Hello everyone, I welcome you all to Physics Wallah, and in this session we are going to discuss the next portion related to our very interesting chapter, which is equilibrium. Now the entire part of equilibrium is about to end. Basically one more lecture is there, and in that lecture I told you earlier that we are going to discuss different type of numerical portions related to ionic equilibrium only. How to deal with the questions if somebody asks that question in JEE mains or in JEE advanced, in case of solubility, in case of buffer solution, in case of salt hydrolysis, how to analyze that question is from that respective part and how to proceed for that particular question. Okay, that part we are going to discuss in the last session. Okay, now in the previous part we were discussing about the concept of salt hydrolysis. We already completed that part. Then the next portion was the introduction of a buffer solution, and the entire part of the introduction of buffer solution is already done. Now basically in this session we are more focused on the calculations related to simple buffer, acidic as well as basic buffer, and buffer capacity and buffer range, and last part is basically the introduction part of solubility as well as solubility product. Okay, so let's start. If I talk about the buffer solution, basically those solutions which try to resist the change in their pH is basically known as the buffer solutions, and you can prepare those buffer solutions by different methods. If I talk about the first classification, in that case, first one is the very easy analysis of a buffer. So let's say I'm mixing weak acid with weak base. In that case, whatever mixture is present, that can actually act as a simple buffer. So in that case, if I talk about the first part, which is the analysis of simple buffer, you can say it is a solution of one compound which is only salt of weak acid as well as weak base. So this is one of the case. I'm not talking about the general cases of buffer. This is one of the case that I'm talking about the simple buffer which has only one constituent containing a salt of weak acid as well as weak base. Now buffer action of such solution can be explained with the help of very simple analysis. Buffer action means if you are adding certain amount of acid, if you are adding certain amount of base, how it's going to be compensated by the entire part of buffer so that it will try to resist the change in their pH, because it's going to change the pH definitely, but that pH change is not that large. It's going to be very small change. Okay, so if I talk about the salt of weak acid as well as weak base, you know that salt is generally taken as CH3COO NH4, which is ammonium acetate as per. Okay, in that case, if I talk about the corresponding ions which are present, you know, in this case we have two ions. First one is acetate, CH3COO negative, and the next part is NH4 positive. So two ions are there, CH3COO negative as well as NH4 positive. When they are present in presence of H2O, you know that H2O is going to feebly ionize. H2O is going to feebly ionize so that they can convert into CH3COH as well as NH4OH. It means in that case salt hydrolysis is going to take place. That was the case, last case of salt hydrolysis. That is the case of weak acid as well as weak base. Both are going to hydrolyze to form CH3COH as well as NH4OH. Now let's say in this particular mixture which contains salt of weak acid as well as weak base, I'm adding certain amount of acid or base. So basically in this particular portion, if you see, this NH4OH is going to be dissociated into NH4 positive as well as OH negative, and this is CH3COOH negative, CH3COOH, which is weak acid, is going to again ionize into CH3COO negative as well as H positive, just like this reaction, and meanwhile H2O is going to be feebly ionized to form H3O positive as well as OH negative. Now the main case, I know that this species is already present. I'm adding H positive in the solution. Definitely that entire part is going to be converted into CH3COOH, but reverse reaction is not that feasible because the CH3COOH is not going to decompose that much easily. So let's say on addition of a small amount of acid from outer medium, let's say I'm using a strong acid, definitely it's going to dissociate 100% and it's going to provide directly H positive. This H positive is going to be compensated by CH3COO negative, which is already present in the salt. and it's going to convert into CH3COH. But reverse reaction is not going to be 100% because CH3COH is going to be ionized very, very less. Now in this case you can say that H positive, whatever H positive I'm adding is going to be compensated by CH3COH, so it's not available for the pH calculation, it's not free for the pH calculation, so pH change is not going to occur that much. Okay, I hope this part is clear. So in this case equilibrium will shift in the forward direction. Similarly, on addition of a small amount of base, which is OH negative from strong base, let's say, what happens in this particular case, this NH4 positive which is already present in the salt is going to take up this OH negative and form NH4OH, but reverse reaction is not true because it's going to be ionized very, very less. If that is true, you can say that OH negative is now not available for the pH calculation. So it means the pH change is going to be very, very less because already certain ions are present which are going to compensate, which are going to use all the H positive, all the OH negative which is present, which is given to the mixture part. Okay, so in case of buffer you can say the most important thing is the presence of that ion which is going to compensate H positive as well as OH negative, which is added from the outside solution. Okay, I hope this part is clear. Now simple buffer solutions have a little significance because their pH can be calculated just like the salt hydrolysis. If you remember that entire formula, pH is equal to half of pKw plus pKa minus pKb. So that part is basically there. Now solution of desired pH cannot be prepared because it is independent of the concentration. There is no term related to concentration, so you cannot prepare a solution of desired pH. So that is the drawback in that particular case. Always remember that is the drawback because it is independent of the concentration. I hope this part is clear. So this is one of the example of simple buffer. Now let's move on to the next part, which is much more relevant. That is the analysis of a mixed buffer. So in case of mixed buffer, definitely more than one type of species are going to be present. Not just salt. It may be possible that some acid is also present. So that's why we have further two classification. First one is acidic and next one is basic buffer. Now, first of all, whenever we are talking about the acidic and basic buffer, mixed buffer, in that case, always remember we have salt along with either we have acid or we have base. That is the most important thing. Okay. And I told you what is the difference between the salt hydrolysis and this buffer solution. In case of salt hydrolysis, equivalents of acid are always equal to equivalents of base. It means both are completely consumed. If both are completely consumed, in that case only salt will be present. If that's the case, if only salt is present, definitely salt hydrolysis takes place. But in case of buffer solution, and mainly in case of mixed buffer solution, the main important criteria is that either equivalents of acid are going to be more than base or equivalents of base are going to be more than acid. If equivalents of acid are more than base, definitely we are talking about the acidic buffer. If the equivalents of base are more than acid, then definitely we are talking about the basic buffer. But how to create this entire part? How can we create a different type of buffer solution? Because in question, we can find 2-3 different lines for the buffer solution, and we don't know like how this is going to prepare a buffer solution. So we should know like what is the criteria for the buffer solution. So first of all, if you are directly mixing weak acid and strong base salt with a weak acid, so for example, weak acid I am taking as CH3COOH. So in a mixture, if a CH3COOH is present along with salt of this acid with strong base, that will be CH3COONA. If directly this part is given, definitely the question is talking about the formation of a buffer solution, because acid is present and some amount of salt is also present. Definitely this entire part will be the buffer solution case, because in case of salt hydrolysis only salt should be present, no acid, no base. Okay. Second, just like that, another case, reverse case, will be if I am having, let's say, NH4OH. So the main criteria is it should have been weak acid and weak base along with its salt with strong component, and its component in that case is NH4Cl. That is another criteria. I hope this part is clear. Now, second case, if this data is directly given, then definitely the question is from buffer solution. It may be possible that question is looking like the reaction between acid and base. So you need to understand what is happening. So in this case, we are having a mixing of weak acid and strong base. Another condition is there. You are mixing weak acid and strong base, but the condition is the equivalents of weak acid are going to be more in comparison to a strong base. If that is so, it means you can say base will be completely consumed. If base will be completely consumed, you will left with one thing, which is weak acid plus salt of weak acid plus strong base. Again you will left with the same thing. Definitely we are talking about the first type formation, but indirect step. For example, CH3COH is there, you are reacting with NaOH. Half equivalent, one equivalent. Definitely it is more. After the reaction, it's going to form half equivalent of this CH3CONA, and this entire part is going to be consumed. It will remain half equivalent. It means acid is present and its salt is present. Definitely we are talking about the buffer solution. I hope this part is clear. Reverse of this entire part, which is, again, I'm using weak base with strong acid. In that case, let's say NH4OH is reacting with HCl. HCl is less, NH4OH is more. After the reaction, HCl will be completely consumed. It will be NH4OH as well as NH4Cl only. Again the same case, that we have mixture of weak base plus salt of weak base plus strong acid. Same condition. Okay. I hope this part is clear. Now it may be asked, sir, let's say I'm using strong acid and strong base, and acid is more, base is less. Can I form the solution in that case? So no, beta, buffer solution cannot be formed in that case, because if you are using a strong acid and strong base, first of all, the ionization or dissociation will be 100% in that case. And if one component is more, definitely H positive will be more in comparison to OH negative. And if you are using OH negative in a certain range, then it can show, because from the titration curves you can compare that at a certain particular pH range it can work as a buffer solution. But again it is very sensitive solution, because on increasing H positive or decreasing H positive, it's going to show a drastic change in the pH, which is you can get from the titration curve of strong acid as well as strong base. So that's why we generally don't prefer that type of solution. But yeah, in a particular pH range it can work as a buffer solution, because the pH is going to remain same in that particular region. Okay, I hope this part is clear. These are the three cases. I hope now the idea is clear how to create buffer solution. Now it's time to discuss about the first type, acidic buffer as well as basic buffer. What is the buffer action, what is the buffer range, and what is the buffer capacity in those cases. Okay, I hope this entire part is clear. Now let's start. I'm talking about the first part, which is acidic buffer. It means in that case the component is weak acid as well as its salt with a strong base. Okay, so the thing is, this is a mixture of a weak acid and its a salt with a strong base. It means you can take CH3COOH with CH3COONA, most common case, or you can take boric acid with borax. Borax is the salt of that boric acid. Now, buffer action of acidic buffer can be explained with the help of a very interesting analysis. Now, always remember that salt is going to ionize 100% because it's always a strong electrolyte. So, if you are talking about the analysis, in that case, this reaction is going to be reversible one. This is going to be reversible one because this is feebly ionized. CH3COOH is not a good or strong electrolyte, but every type of salt is a very strong electrolyte. So it's going to completely ionize into Na positive as well as CH3COO negative. Now one thing which I want to mention, you can see there is a presence of CH3CO negative here, CH3CO negative here. Common ion is there. If common ion is present on the product side, it means the product amount is going to increase. According to Le-Chatelier principle, it has to compensate, it has to decrease that amount. It means the reaction will go in the backward direction, which proves that this entire part CH3COH is going to be feebly ionized. I hope this part is clear. If I talk about the water, you can again see this reaction is going to be like this, feebly ionized, H positive as well as OH negative. Now the main part, when a strong acid is added in the solution. So what happens if I'm adding strong acid? What happens if I'm adding strong base? Whether the pH is going to be changed or something is already present to compensate the entire part. Let's find out. So when strong acid is added in the solution, which is H positive, directly H positive is added, which will combine with CH3COO negative, and it is present in both the two species, CH3COO negative. So basically the CH3CO negative is going to combine with H positive, upcoming H positive, to form feebly ionized CH3COH, which is also suppressed by common ion effect. So this CH3COH is going to take up H positive and it's going to be converted into CH3COH, which is a weak acid. It's not going to be again dissociate into CH3CO negative as well as H positive, because its dissociation is already suppressed just because of the presence of common ion, which is this entire part. Okay, I hope this part is clear. Again, this is the first case. This is the first case which proves that if I am adding acid, it's going to be compensated very easily because of the presence of CH3CO negative. Next part, again when a strong base is added, so CH3COOH is present. Again, if you are adding base, it means this is an acid, na? So this acid is going to react with that particular base to form salt again. So what happens when a strong base is added in the solution? It will attack on the unionized acid to form feebly ionized H2O molecules, just like this reaction. So this is going to form CH3CO negative again as well as H2O. It means if you are adding OH negative, it's also compensated in the solution, which shows that it's going to resist its pH change. Okay, it's going to resist its pH change. So the entire part is very easy. That CH3CO negative species is going to take up H positive to form CH3COH. The CH3COH is going to take up OH negative and then form CH3CO negative. So that is the buffer action. So it happens like this. If you are adding acid, it is going to be compensated. If you are adding base, it's going to be compensated very, very easily. I hope this entire part is clear. I hope this entire part is clear. Now, if I talk about the pH calculation in that case, you know that first part is going to be the reversible reaction, but the second part is going to be the 100% dissociation. So CH3COH is going to be feebly ionized and its ionization is also suppressed by the presence of common ion, which is a CH3CO negative. Now, if you remember exactly, that we discussed about one calculation, that if something is coming from the strong electrolyte, it has more contribution, so it's going to change the concentration of this common ion with whatever present in the solution. So that is the first part which you have to understand. So what happens? So we can say that CH3CO negative is directly coming from the salt, which is a major component, because CH3COH is very less ionized. Now CH3COH concentration is coming from acid only. Okay, now these two things are very important. So if I'm writing the same equation, which is a CH3COOH is going to ionize feebly to form H positive plus CH3COO negative. Just because of this entire process is having very low degree of dissociation, so you can say alpha value is very low. So you can say that whatever this amount is coming, this is coming, or you can say major contribution is coming from salt, or you can say strong electrolyte. So if I talk about the expression of this entire part, I can say K will be equal to concentration of H positive as well as CH3COO negative divided by CH3COOH. Okay, I hope this part is clear. Now you can rearrange the entire part with respect to H positive. So H positive will be equal to Ka multiplied by the concentration of CH3CO negative divided by CH3COO negative. So that is the expression we are looking for. Now in this expression you can say this entire part is from acid itself, but this is coming from salt because it is feebly ionized, its concentration is not that relevant, but strong component is already there, which is CH3 COONA. It's going to be dissociate 100% to form CH3COO negative plus Na positive. So this part is very much relevant. Now if you take the negative logarithm of this entire part, you can take minus log H positive will be equal to minus log Ka. Log A into B is log A plus log B. So minus sign is always there. So minus log Ka minus log concentration of CH3COOH. Now this part is log A upon B is log A minus log B. So minus sign is already there. It will become positive. Now in this entire calculation, this log minus log of H is nothing but pH. This entire part is nothing but pKa, and log minus log, or you can say plus log CH3COO negative minus log CH3COOH. Log A minus B is equal to log A upon B. So finally you can write down the equation that pH will be equal to pKa plus log CH3COO negative upon CH3COOH. Or you can say that the concentration of conjugate base divided by acid, or basically this conjugate base is coming directly from salt. That means the final equation becomes pH is equal to pKa log concentration of salt upon acid. That's it. And this equation is actually known as Henderson-Hasselbalch equation. Okay, this equation is Henderson-Hasselbalch equation. Hasselbalch or Hasselbalch, I'm not sure. But something like that. Okay, it's Henderson Hasselbalch. LCH hai. I'm not sure. It's going to be Balch or Belch. So just leave it. If you know the actual pronunciation, then just let me know. Okay. So that is the most important equation. This is the equation which is relevant in the pH calculation. Now you are thinking like, sir, questions are direct, we can use the formula. Why you are dealing with such issues, like why we are deriving the entire part? We discussed about the salt hydrolysis in the same way. You discuss the entire part. What is the actual relevance, like why we are doing this entire part? So let me tell you the actual analysis of the entire part. Whenever you are performing an acid based titration you all know. I'm pretty much sure you all know what is the concept of titration. So whenever you are dealing with the particular titration between acid and base, at every stage these processes are occurring. When initially acid is present only, it is only acid. When certain amount of base is added, it becomes buffer solution. So pH is not going to change. When both the equivalents are equally like both the equivalents are equal of acid and base, that time the solution becomes salt hydrolysis solution, and pH can be calculated directly with the help of that formula. After the addition of some amount, base is going to increase, acid is going to be compensated, and last entire amount of acid will be vanished and only base will remain. So at every stage you are looking at the buffer solution, creation of buffer solution, salt hydrolysis, then buffer solution. Drastic points are acid as well as base. So this is the entire flow of a particular titration. So how you are going to calculate the pH of that solution? So with the help of these data only, if you know these things, that when the equivalents are equal, salt hydrolysis is there, so definitely pH can be calculated with the help of salt hydrolysis only. If equivalents of acid are more in comparison to base, salt will be formed, definitely that is the case of buffer, so we can calculate pH according to that particular part. So that part is relevant when you are dealing with acid based titration and you want to calculate pH at every stage. Okay, so that is the idea behind the entire part. Okay, now if we increase the concentration of given salt, so you can see if the salt concentration is going to be increased, it means the pH is going to increase, it will become more and more basic. If I am adding the concentration of acid, definitely pH is going to decrease. So always remember this entire part. If we increase the concentration of given salt, pH is going to increase. If we increase the concentration of acid, pH of the buffer is going to decrease. If the concentration and volume of salt are given in terms of N1V1 and N2V2, then you can calculate by the simple formula. Instead of concentration, now you can use N2V2 upon N1V1. Okay, I hope this part is clear. N2V2 is the concentration volume of the salt, N1V1 is the concentration volume of acid. So mixture of weak acid and strong base solution can also act as an acidic buffer if the value of N1V1 of weak acid is greater than the value of N2V2 of strong base. Okay, I hope this entire part is clear. I hope this entire part is clear. Okay, same type of thing, acid should be more in comparison to base, that's it. Okay, so this is the entire part related to the analysis of your first portion. Okay, just have a look. Okay, now the next part is going to be very interesting, which is the concept of basic buffer. Now in this particular case, you are using weak base and it's salt with strong acid. So for example, I'm using NH4OH with NH4Cl, or I'm using glycine with a glycine hydrochloride, which is its salt. So you can take different examples with the help of that part, and rest of the part is easy. Now what about the buffer action? First of all, if I talk about the NH4OH, it's going to be the reversible reaction and it is feebly ionized. Definitely NH4Cl, being a strong electrolyte, is going to ionize completely into NH4 positive as well as Cl negative. H2O is also going to be feebly ionized into H positive and OH negative. Now just because of the presence of NH4 positive, which is a common ion, the entire part of this concentration is going to increase, and main contribution is coming from this strong component. This is strong component. Now the reaction will go in the backward direction, that's why we have feebly ionized NH4OH. Now talking about the buffer action in that particular case, let's try to decode that part. What happens when a strong base is added in the solution? When a strong base is added in the solution, it means OH negative is now present. So NH4 positive is already there. So NH4 positive is going to take up this OH negative, which is directly coming, and it's going to form NH4OH. But the reverse reaction is not that prominent, so it's going to be feebly ionized into again NH4 positive and OH negative. So OH negative is already compensated, it's not available free, so there is no change in the pH, or that much change in pH is not possible. Now what happens if I'm adding H positive? So this entire amount of base which is formed in the reaction is already there. This is going to take up this H positive, and again it's going to be converted into H2O as well as NH4 positive. Now this H positive is also compromised, it's also compensated by NH4OH, because base is there, base is going to take up or react with acid definitely, so that reaction is also possible. It means now when you are adding H positive or OH negative, both are not available freely, so it means there is a very less change in the pH. Now what about the pH calculation in that particular case? It's again very easy. So we have two species, first one is NH4OH and next one is NH4 positive. This NH4 positive is going to take up all the base to form NH4OH. This NH4OH being a base is going to react with acid to form NH4 positive. So this entire part is the buffer action. Okay, now the next part. First one is NH4OH is going to be compensated, or it's going to ionize very little, but the main contribution of this NH4 positive is actually coming from this strong electrolyte. This is strong component, but this one is weak component. This one is weak component. So I can say that Kb of this entire reaction will be the concentration of NH4 positive OH negative divided by NH4 OH. That will be the part. From that calculation, you can say that the OH negative concentration will be equal to Kb into concentration of NH4 OH divided by concentration of NH4 positive. So this one is coming from base, but this is coming from salt only, because that is a major component. I hope up to that part everything is clear. So you can take the negative logarithm and that will be the POH, and again for the calculation of pH you just have to subtract the entire part from 14. So that is another scenario. So what happens in that case, POH will be pKb plus log salt upon base, because if you use this reaction, that will be minus of log Kb, sorry, minus of log OH negative will be equal to minus of log Kb, okay, and then minus of log concentration of NH4OH divided by NH4 positive, that will be there. It means this entire part is POH will be equal to PKB, and if I'm taking plus sign here, so that will be reversed. It will be NH4 positive divided by NH4OH. Okay, that is the equation. That is POH is equal to PKB plus log salt upon base. So that is the equation. Now if you want to calculate the pH, pH will be 14 minus POH. I hope this part is clear. Just have a look at it. Okay. Now, the property of a buffer solution to resist its alteration in the pH value is known as the buffer capacity. So now we are talking about the next term, which is buffer capacity. So basically buffer is definitely a solution which is trying to resist the change in the pH. So basically the property of that particular buffer solution to resist alteration of its pH is basically known as the buffer capacity, and the more mathematical definition in that case is very much relevant. So buffer capacity is basically the number of moles of acid or base added in 1 liter of the solution so as to change the pH by only 1 unit. That is actually known as the buffer capacity. Okay, it means buffer capacity, which is represented by phi, will be equal to number of moles of acid or base added in 1 liter solution divided by the change in pH. Okay, that will be the buffer capacity. Very interesting formulation, very interesting formulation related to the entire part. Okay, so always remember this formula for buffer capacity. Okay, now it means if this number of moles of acid and base are more but the change is less, or for 1 unit if these number of moles are very much high, it means buffer capacity is going to be very high, and that solution, buffer solution, is going to be the greatest one. So higher the buffer capacity, better will be the buffer solution, because it will require maximum amount of acid or base to change the pH by only 1 unit. Okay, so that buffer solution will be great. Okay, I hope this entire part is clear. A very interesting point indeed. Okay, I hope this part is clear. Now, for maximum buffer capacity, of a given buffer, concentration of salt should be equal to the concentration of acid or base. So if this entire part, if the ratio is actually equal, so in that case you can say that will correspond to maximum buffer capacity. And there is a buffer range. There is a buffer range. So a buffer solution always work in a buffer range of a pH which is pKa plus minus 1. So this entire part, because that is 1 will be there. If you remember the formula, so let's say, sorry, if I talk about the formula of a pH, that will be equal to pKa plus log salt over acid. That was the formula. That was the formula. So if a pH actually becomes equal to pKa, that will be the maximum buffer action, because this entire part is already equal. This entire part is already equal. Now what happens? It may be possible that pH will be equal to pKa plus minus 1. If that is the range, that is the range of buffer solution. In that range only buffer can work very easily, because we are talking about the unity change in the pH. That is the entire part of buffer capacity. So always remember that a buffer solution work in a buffer range of pH from pKa plus 1 to pKa minus 1. Okay, that is the entire part. Or you can say a buffer solution work between the concentration of salt upon acid or base, and that is 0.1 to 10. In between that entire part, 0.1 will give minus 1 value, 10 will give plus 1 value. So that is another aspect of the entire portion. If that portion becomes 0, that is the maximum buffer action. That is the maximum buffer action. But it can be 0.1 upon 1, that is pKa minus 1, 10 upon 1, that is pKa plus 1. Okay, so both the things are there. So this entire portion is going to be very, very important. Always remember, this is going to be very helpful whenever you are dealing with the questions of buffer solution. Okay, I hope this entire part is clear. I hope this entire part is clear. Now next thing is basically the concept of solubility. So today we are not dealing with the calculation part of buffer solution. That part we are going to discuss in the next class, because next class is only numerical analysis, nothing else, only and only numerical analysis. So I want to start the concept of solubility, because that is the only part which remains in this entire chapter. With the help of question analysis part, we are going to decode the idea of titrations also, like how you are going to deal with the titrations. But if the titrations are if we are unable to complete the titration part, definitely that part will be covered in the redox reaction only. Okay, so don't worry. Now if I talk about the concept of solubility, so always remember, solubility is nothing but at a constant temperature. At a constant temperature, the mass of a solute or the electrolyte which is dissolved in the 100 gram of its solvent in the saturated solution state is known as the solubility. So maximum amount of a solute which can be dissolved in a given amount of a solvent, generally it is 100 gram. So that part corresponds to the solubility, because we are making a saturated solution. So number of gram mole of solute dissolved in 1 liter of water at constant temperature is also known as solubility of that solute. Okay, so that depends upon the criteria which you are using, either in terms of molarity or in terms of simple gram or amount of a solute which is dissolved in 100 gram of the solvent. Okay, so that is the basic part of solubility. So there are different salts we can use, there are different electrolytes we can use for the solubility part. There are some salts which are going to be completely dissolved very easily. Those are completely ionized and they are going to perform very well in the solubility criteria. But there are different type of salts which are very less soluble, which are partially soluble. Those parts are relevant to us, because we are not concerned about the 100% electrolysis. We are not concerned about the 100% dissociation. We are concerned about the dissociation which is partial dissociation, where you can establish the equilibrium, where the reaction will be reversible, and that part is much more relevant. Okay, so that's why we are more concerned about the partially soluble salts. Okay, now in this particular case, the solubility of a solute in terms of mole per liter, if you are explaining the entire part in mole per liter, so solubility of solute which is in gram per liter divided by the molecular weight of the solute, nothing but number of moles of the solute divided by the volume of the solution, same part, okay. I hope this part is clear. Now, if I talk about the solubility product, it is slightly different. So, it is the product of the ionic concentrations of the ions of a binary solid electrolyte in a saturated state at constant temperature. So, first you have to establish that saturated state, then only you can talk about the ionic concentration of the ions of a binary electrolyte, of a binary solid electrolyte in the saturated state at constant temperature, because these things are temperature dependent. If you are changing the temperature, you can convert saturated solution to super saturated one. So definitely the solubility entire concept depends upon the temperature also, okay. Now if I talk about the solubility in that case, so let's say the solubility of a compound which is AXBY be S mole per liter. It means if more than S moles are dissolved in a solvent which is 1 liter, only S moles will be soluble, rest part will be insoluble. So that is the basic idea about the solubility. I hope this part is clear. Okay. Okay. Now it's time for the calculation. So basically, let's say I'm starting with the binary salt, which is AB. This is the insoluble salt. Let's say I am dissolving the entire part into solvent. So that becomes AB, unionized saturated solution. So from insoluble part, it's going to be converted into saturated solution. Something of this entire part is going to be dissolved, but in that particular case, a specific amount is going to be converted into ions, which converts into ionic concentration. The rest part will be unionized as it is. So eventually it's going to form A positive as well as B negative ions. Now if I'm using the law of mass action in this entire case, I can say, because this reaction is going to represent the reversible type reaction, so K1, a constant, will be equal to concentration of A positive B negative divided by AB. Although AB is not going to change, because we are talking about the insoluble part which is converting into saturated solution, then it's going to be converted into ions. So this AB is going to remain constant. So K1 into AB is another constant, will be equal to concentration, ionic concentration of A positive as well as B negative. That is basically the solubility maximum amount which can be converted into ions. So that is actually equals to KSP. So this entire part K1 into AB is nothing but the solubility product. It is known as solubility product. KSP is the solubility product. Okay. So definitely the solubility product depends upon the stoichiometry. Just like any other constant, equilibrium constant. So KSP increases with increase in temperature. First part, because it is temperature dependent. If the temperature is going to increase, the ionization is going to increase definitely. So more amount of A positive and B negative will be present in the final state. Definitely in that case, KSP is going to increase. In a saturated solution, always remember KSP will be equal to the product of ionic concentration of A positive as well as B negative. In an unsaturated solution, KSP will be more than their ionic concentration. KSP will be more. It means more solute can be dissolved. Now, in case of supersaturated solution, this ionic concentration will be more. It means precipitation will start to occur. Definitely. Temperature is responsible for the formation of this supersaturated solution. But if we are lowering the temperature, definitely it will start the precipitation process. Okay. So these are few basic points which you need to understand. Now, for any type of general reaction, let's say we are talking about AXBY. It's a binary compound. AXBY, if you look at it, AXBY. Generally, these parts represent their charges. So we have one species which is A, Y positive and B, X negative. Now, how many atoms are there? X atoms are there. So X atoms of AY positive and Y atoms of Bx negative, they are present. It means this is the final equation. This is the final equation. Now solubility product for that type of equation will be concentration of this entire part raised to the power its stoichiometry multiplied by concentration of this part raised to the power by their stoichiometry. Now in this particular case, you can express Ksp in this term, Ksp in this term. But if you want to express the entire part in terms of solubility also, so you can say solubility is also stoichiometry dependent. So let the solubility of this salt, let the solubility of salt is S. Okay. This at a particular temperature is S moles per liter. So initially it was S, nothing was there. After some time, this was completely consumed. Whatever maximum amount can be consumed, so that part is gone. It is going to form XS, it is going to form YS, just like the concentration C minus C alpha, and C alpha. So if stoichiometry is there, you have to mention the stoichiometry also. Okay. Now you can put this entire value here in this equation, and Ksp will become x raised to the power x into y raised to the power y multiplied by s raised to the power x plus y. But it is looking like something is missing in this particular case. Let's try to apply two different type of binary compounds. How to understand this entire part? Okay. So I'm starting with 1:1 type. 1:1 type. So let's say I am starting with AgCl. It's going to be converted into Ag positive as well as Cl negative. Cl negative. Initially it was S 0 completely consumed S as well as, because stoichiometry is same. So in this particular case, I can say Ksp will be equal to concentration of Ag positive raised to the power 1, Cl negative raised to the power 1. So that will be S into S, that is S square. I hope this part is clear. This is for 1:1 type salt. 1:1 type salt. Okay, nothing fancy. In case of 1:2 or 2:1 type, 1:2 or 2:1. So in this case, let's say I am using PbI2. It's going to be converted into Pb2 positive plus 2I negative. Initially it was S, nothing was there, completely consumed S, and it is a 2S. Okay. Now if I am writing the expression of Ksp, that will be the concentration of Pb2 positive and concentration of I negative raised to the power 2. Stoichiometry is there. Now put the values. That will be S into 2S raised to the power 2. That will be 4S cube. That is your Ksp. That is your Ksp. I hope this part is clear. I hope this part is clear. For 1:2 or 2:1 type. Okay, 2:1 type. Now 1:3, AB3 or A3B. AB3 or A3B. So in this particular case, I am using, let's say, Fe. Cl3 is going to be converted into Fe3 positive plus 3Cl negative. S, nothing, S and 3S. Done. In this particular case, you can say that Ksp will be equal to the concentration of Fe3 positive Cl negative raised to the power 3, stoichiometry. Now put the value. That will be S into 3S raised to the power 3. That will be 27S raised to the power 4. I hope this part is clear. That will be the Ksp in this particular case. Okay. There are various applications of this Ksp also. That part also we are going to discuss. Various applications of Ksp are there. Okay. You are going to use that entire part in qualitative analysis, how you are going to use the solubility of a particular ion and try to form a PPT of that particular part. A very interesting analysis there. Okay. Next thing is 2:3, A2B3 or A3B2 type. So in this particular case, we have, let's say, Al2SO4 thrice. It's going to be converted into Al3 positive. How many Al are there? 2 Al are there, and 3SO4 2 negative. 3SO4 2 negative are there. Initially it was S 0 completely consumed. It will be 2S, it will be 3S. Okay, that you have to do in every case. Now, if I talk about the Ksp, that will be the concentration of Al3 positive raised to the power 2 is its stoichiometry, and SO4 2 negative raised to the power 3 its stoichiometry. So if I put the value here, it will be 2s raised to the power 2 and 3s raised to the power 3. So KSP in that case will be 2 2s are 4, 27, 54, 108. That will be 108 S2 S3 S raised to the power 5. That will be the final answer. Okay, so that's how you can deal with the calculation of KSP with solubility. Okay, so that is the solubility product in terms of solubility. I hope this entire portion is clear. I hope this entire portion is clear. So this is all about the calculation of KSP in various cases. We have discussed about that calculation, like how to deal with that calculation related to KSP only. Okay, now let's try to decode one or two questions related to the buffer part also. Meanwhile, we can solve certain questions. So okay, so we were talking about the buffer capacity earlier. So if I talk about the question, you can see when 2 moles of HCl is added to 1 liter of an acidic buffer solution, its pH changes from 3.9 to 3.4. Find the buffer capacity. Very interesting, very simple question. So in that case, the buffer capacity will be number of moles of HCl required in liter solution, which is 2 moles, divided by the change in pH. Change in pH is 3.9 minus 3.4. That will be the change. So I guess that will be equal to 2 divided by 0.3. This will be 0.5. So this is going to be 0 and that will be 4. Buffer capacity will be 4. So one direct question related to this entire part. Very interesting, very simple question. Very simple question. Okay. Okay. So find the pH of 10 ml of 0.1 molar CH3COOH plus 10 ml of 0.1 molar NaOH. K of the acid is 10 raised to the power minus 5. Okay. So basically in this case, if I'm using CH3COOH with NaOH, it's going to form CH3COO Na plus H2O. It's an interesting question. So first part is, here we have a 10 ml and 0.1 molar. In this case again we have 10 ml, okay, and 0.1 molar. If you calculate their millimoles, that will be 0.1 multiplied by 1, that is 1 millimoles are there of acid, 1 millimole of base are there. If both are equal, both are going to be completely consumed, and eventually both are going to be completely consumed and they are going to form 1 millimole of salt, and total volume will be 10 plus 10, which is 20. So V total becomes 20 ml. Now this question is not from buffer because both are equal, both are completely consumed. Now it is the case of salt hydrolysis. It is the case of salt hydrolysis. In case of salt hydrolysis, you easily know how to calculate the pH. So pH will be equal to 1 upon 2 pKw plus pKa plus log C. That will be the entire formula. pKw you already know. pKa will be, Ka is there, so minus of log Ka, which is pKa, will be equal to minus of log 10 raised to the power minus 5. That will be 5 only. So you know this thing. So just put the value 14 plus 5 plus log C. Log C is 1 millimole present in 20 ml solution. So you can easily calculate the molarity in this case. So that is a case of salt hydrolysis. That is a complete case of salt hydrolysis. That is a complete case of salt hydrolysis. Okay. Now, so one more question is there, I guess. This question is there. This question is there. An acidic buffer is obtained on mixing. So these type of questions can be generally asked in direct examination, like in JEE main or Neet examination. These questions can be easily asked. So that calculation you already know. I told you, if the amount of weak acid or weak base is more in comparison to strong component, definitely salt will be present. as well as the weak acid or weak base will be present. That is the case of buffer solution. So in case of acidic buffer, you need weak acid which is more than a strong base. So this is the only case. We have, let's say, 100 ml of 0.1 molar HCl and 200 ml of 0.1 molar CH3COONA. So basically CH3COONA, if you talk about the 200 ml, so we have a 0.2 20 millimoles of CH3COONA, and in this case we have only 100 ml, means 10 millimole of HCl. This CH3CO negative is basically already present. It's going to react with H positive directly coming from the acid, and it's going to form corresponding acid. So acid is there, its a salt is there, definitely that part is your buffer solution. Okay, I hope this entire part is clear. It's a very interesting question. You can try it by yourself. I'm just giving you the answer here. It's going to be D option, but you can try rest of the options by yourself. Okay. So I have mentioned some more questions related to the calculation of a buffer as well as the pH calculation part, and remaining part we will discuss along with the concept of solubility. That part we are going to discuss in the next section. Okay. So I guess we have completed the entire portion. This is the theoretical portion. I have not included so many questions in this session because it's very relevant to understand the concept of solubility first, then some practical applications of solubility. So next class is going to be the most important class of ionic equilibrium, I must say, and very important class, because in that class we are going to discuss n number of numericals related to mains, advanced, NEET examination, as well as we are going to discuss the portion of acid base titration. Okay, so that's all from my side. Thank you so much.